Great. Thank you very much. I'd like to first thank the organizers for putting together such a wonderful program this week. The subject is sort of sufficiently close and sufficiently far from what I know, so I've learned a lot. And it's, of course, always great to be in Vienna. So I'm going to talk about, as our session chairperson just told us, late time tails. I'm going to first motivate the problem, and then I'm going to tell you the result. But already I want to sort of emphasize what I want to do here is I want to understand the wave propagation on asymptotically set spacetimes. And the emphasis is I want to think about there as spacetimes which are dynamic and also spacetime which have odd spatial dimension. I'll talk about these both of these aspects a little bit more very soon. And I want to sort of find a way to completely understand them. If you give me some waves, I want to understand what the tail would look like. So the result I'm going to talk about is joint work with Songjin Oh from Berkeley. At the moment, the paper is still not posted, but hopefully soon. Okay, so let's begin. So as I said, I'll start with motivation. The motivation comes from Strong Cosmic Censorship Conjecture, which I'll explain. And then I'll try to explain late time tails. I'll first try to explain late time tails in maybe a slightly more familiar setting, which is when the background is not dynamic, when the background is stationary. And these tails are often known as Price's law tails. And then I'll tell you something about late time tails on dynamic spacetimes. So all of these sort of, you should think as sort of examples of trying to understand late time tails. And then I'll tell you really what the main result is, what's the main theorem on trying to understand late time tails. And then hopefully I can tell you some ideas in the proof. Okay. So let's start. So the story begins on something that a priori doesn't seem to be related to late time tails. Oops, okay. And this is the story about strong cosmic censorship conjecture. So let me start by considering these two examples of black hole solutions. So I've drawn for you the Schwarzschild black hole solution and the Kerr black hole solution. And these are explicit solutions to the Einstein vacuum equations. So you can write down explicit metric, which I have not done here. And then you can check that they solve the Einstein's vacuum equations. So here there are sort of two parameters. There's a parameter m, which is about the mass of the black hole. There's a parameter a, which is the specific angular momentum of the black hole. If a is equal to 0, then you get the first picture, which is Schwarzschild black hole. So this is part of the Kerr family. But if a is not 0, then you get the second picture. So how should I think about these pictures? So if you have not seen these pictures, you can think of the cartoons as saying the following. So I have a space-time. So space-times, these are 3 + 1 dimensional, but because of my lack of ability to draw, I have to draw only 1 + 1 dimension. So in the Schwarzschild case, this is sort of really honest. There's a spherical symmetry, so I just model the spherical symmetry, and I do a conformal compactification, and then I have a picture that looks like this. And the way you should think is that this is a solution to the Einstein's vacuum equation arising from some data. So let's say the data is posed here. The data, you should think that on each far away end, this is an asymptotically flat end. So away here, you have something that looks like Minkowski space. But then the global structure is very far away from Minkowski. In particular, there's a region which is a black hole region here. Okay? And the Schwarzschild black hole has the property that if you enter the black hole, you'll see what's known as a singularity at r = 0. And if you're an observer going through that singularity, you'll be infinitely torn apart. This is in contrast to the solution Kerr, right, which is of course similar. You have initial data, okay, and then you have far away region, which is asymptotically flat, looks like Minkowski. Again, you have a black hole region, right, in which you cannot escape. However, there's no singularity whatsoever in the maximal development of the data, and in fact, you have a smooth Cauchy horizon. So if you are an observer, you'll just get to the end of spacetime, which is smooth, and nothing really happens to you. And it turns out that, well, you might think for the observer, of course, this picture is much better for him or her. However, sort of from the point of view of the initial value problem of the Einstein's equation, it turns out that this picture is much less good than this picture, precisely because sort of the space-time, the maximal development breaks down, but there's no blow-up of any sort. And therefore, you can extend the space-time in ways which are not unique, but you still solve the Einstein's equation, causing a problem to determinism. So because of this, there's a famous conjecture, now known by the name of Strong Cosmic Censorship Conjecture. And in its modern formulation, it says that, well, what you saw there in the Kerr case, when A is not 0, shouldn't really be there. It should be some non-generic thing. So if you perturb, it should go away. So the conjecture roughly says that if you look at the generic data, so if you don't look at the particular Kerr data, then in fact, if you look at the maximal solution, then it should be inextendable as a suitably regular Lorentzian manifold. So some sort of singularity should arise. So whatever you saw for rotating Kerr, that's not expected to be generic. And in fact, small perturbation of Kerr is expected to lead to singularities in the black hole interior. So by now we know the picture is actually a bit more subtle. So this is a result joined with Mihalis Dafermas 6 years ago. What we showed is the following. So suppose you don't have exact Kerr, but suppose you have a solution that in the exterior region converges to Kerr. Okay, so you have, this is Kerr, but if instead of having exact Kerr, you have something in the exterior which converges to Kerr. Okay, and if you have that, then in fact, well, remember that this conjecture tells you that you expect the interior of the black hole, in particular the fact that you have a smoothly extendable Cauchy horizon, to be unstable. But the theorem tells you that in fact there's a sense that it is stable. What we proved that is that you still have a null Cauchy horizon, so the picture looks like the second picture instead of the first picture, and moreover the metric you can continuously extend to the Cauchy horizon, and in fact everywhere inside at least close to time like infinity, everything is close to Kerr. And if you combine this result with results about stability of Kerr exterior, that is to say statements about if you perturb the exterior of Kerr, and then the exterior of Kerr is going to converge to a nearby Kerr exterior, then you can start with those and then use this result, saying because the exterior is going to converge to Kerr, and therefore the interior will also have a null Cauchy horizon, then you can actually say that if you look at perturbation of Kerr, right, Cauchy data, then in fact you will have a picture that looks like Kerr. So in particular, this you can do for A very small, using the recent works on stability of Kerr, and I believe there will be a talk later this week related to the stability of Kerr, so I'll refer you to the talk. So I should point here, is that the problem? To the talk of Teixeira da Costa on Thursday about this problem. So let me just say again the theorem I just told you in pictures, right? So suppose you have an exterior region which converges to Kerr, the interior you look like Kerr, you have a Cauchy horizon, you have something that looks like Kerr, and if you combine with the stability of Kerr exterior, then you would have, if you have a small perturbation of Kerr, at least when A is small, then the exterior would converge to Kerr, and then okay, everywhere inside looks like Kerr. Of course, then, well, from the point of view of cosmic censorship conjecture, this sort of is not quite good because, okay, I do expect there to be a singularity, but turns out the answer to this, the whole problem is a bit more subtle, which is even though there's a Cauchy horizon, which I told you that the metric remains regular, in fact, one would expect that if you look at generic small perturbation, that the Cauchy horizon actually, even it exists, is singular. So it's not as good as what you actually see in Kerr, and in particular, there's a certain sense that you should not be able to extend the solution beyond the Cauchy horizon. Okay. And it is for this story that now late time tells becomes relevant. So remember, I told you in the theorem with Dafermas that if I know that the exterior region converges to Kerr sufficiently fast, right, then I know the interior has a Cauchy horizon. And to prove this conjecture, one expects that one has to say that, well, the exterior region in fact converged to Kerr sufficiently fast so as to have a Cauchy horizon, but it also has to converge sufficiently slow, so that something has to be singular. So one expects this has to do with some lower bound of convergence in the exterior of black hole, and because of this, one would be interested in trying to understand precise late time tells of approach to Kerr. So there are a couple of reasons that you sort of expect the lower bound on the approach of Kerr to be relevant to this conjecture. So one of the reasons that you see this is we have guides from trying to think about an analogous conjecture in a strictly symmetric case. In that case, if we look at a certain sort of strictly symmetric nonlinear model, we know that if we understand the lower bounds, right, like what we want to understand here, then we actually would have singular Cauchy horizons. So in this story, the analogous result of the continuous stability of Cauchy horizon was established by Raniansky, and in some works with Sung-Jin Oh a few years ago, we established a certain lower bound, which then in particular tells you that the Cauchy horizon is singular, and more recent work shows that if you have a more precise understanding of the lower bound, then you have a more precise understanding of the singularity inside the black hole. And another sort of guide, to tell us that lower bounds are relevant to this conjecture, comes from a problem which does not require symmetry, but they are linear. So you can try to think about certain linear instability results of Kerr. For instance, you can try to look at the linear wave equation on Kerr, or you can try to look at the Tukhorski equation on Kerr, which is closely related to linearized gravity on Kerr. And there, right, what you can show is that, well, there would be an instability, and the linear instability is strongly related to certain lower bounds that you can prove in the exterior region. So I've cited a bunch of results here. So they are separated by a semicolon here. And what it means is that the first kinds of result tells you that if you have a lower bound in the exterior, then indeed the Cauchy horizon is singular. And for the result which is after the semicolon, these are results which tells you that, well, the lower bounds that you want for this result, they indeed holds for generic initial data. Right? So we have some guide, at least from closely related problem, that what we really want to understand would be try to understand lower bounds. Okay, and this is what we would like to understand in this talk. So the goal of this talk is I want to give a general theorem to try to compute tails for waves on asymptotically, flat spacetimes well, at first it's just dimension 3. That's the relevant case. I'll explain why I am interested in all the greater than or equal to 3 odd dimensions. So already at this point, one can note that actually the odd dimension case is quite amusing. So if you think about just wave propagation on, let's say, odd dimension with three or higher odd dimensions, if you think in Minkowski space, of course, in Minkowski space, there's this very funny phenomenon, which is known as the Strong-Huygens principle, which tells you that if you have wave propagation, right, if you start with compactly supported initial data, right, because of Strong-Huygens principle, so everything would just stay inside these two cones, right? So if you want to look at lower bounds, if you just go here, right, look at lower bounds, there's no lower bound whatsoever. If you look at odd dimensions, this is of course very different from even dimension. If you look at even dimension, of course there is, even if you look at Minkowski, there's already a tail. And in fact, in even dimension, that tail, one expects that already to be stable. If you perturb, let's say, your spacetime, you will still see that tail in even dimension. So there are some recent results which sort of indicate that. Let's say, in particular in stationary spacetimes, so very recent work of Gaish, Hinz. And in fact, you can also see somehow this very special thing about odd dimensions in some work which is not exactly about wave propagation of asymptotically spacetime, but instead on sort of more general asymptotically conical spacetime by Gullimore, Hassel, and Sakura, which tells you that there's something really quite special about the greater than 3 odd dimensions. It has to do with something about the eigenvalues of even dimensional spheres. Okay? So let me just say that. So right. So there's something particularly interesting about odd dimensions because already on Minkowski you have decay, which is very unstable, which you have a Strong-Huygens principle, and in general, it takes some work to try to understand exactly what happens in these dimensions. Okay, and of course, our motivation finally is not just to get some results about tails. We really want to go back to the problem of strong cosmic censorship. And if we want to go back to the problem about strong cosmic censorship, it is important to have results about tails, which is sufficiently general, which in particular allows for dynamical spacetime, because the spacetime that converge to Kerr, they are of course dynamical, and also allow us to think about nonlinear equations, because of course Einstein's equations are not linear. And let me explain sort of in one word why I want to think about sort of all high dimensions. The reason is that, well, of course, I know that the Einstein's equation, I shouldn't really just think of it as a scalar wave equation. I should think of linear linearized gravity or Kerr, these are sort of high spin fields. But so far, I'm not thinking about anything really about high spin yet. But I want to sort of think of high dimensions as, let's say, a poor man's high spin field. There's some relation between these. Alternatively, I want to think still in 3 dimensions, but higher spherical angular modes. So think of high spherical harmonics. That can also be sort of a proxy of high spin fields. So I want to think about this problem of tails in this generality. So roughly, the theorem that I'm going to tell you takes the following form. So the theorem, I'll be more precise later on, is that you can give me a wave equation. So there are certain restrictions, of course, what's allowed for the wave equation. They can be nonlinear, they can even be quasi-linear, on asymptotically flat spacetimes with odd dimensions. So if you give me a solution, I have to already assume the solution decay. Okay, so let's say I don't want to think about issues about, let's say, well-postedness of the quasi-linear wave equation. Suppose it's already global, suppose it's already decayed, let's say, a little bit. Then I want to tell you that there's a way to compute what the sharp decay rate is. Okay? This is similar as I stated here. It's not exactly honest. For instance, I can't see phenomenon like Strong-Huygens principle, etc. But I'll be more precise as we go on. Okay? So roughly, the goal is to really find a way to just compute what the sharp decay rate is in potentially dynamical and nonlinear situations. Okay. So I'll try to explain that result, of course. But before that, let me just have an aside. What I've told you is a story about Kerr black holes. So these are black holes which are asymptotically flat. And there, the expectation of what you want to look for, it's quite clear that we want to look for sort of polynomial upper and lower bounds. But it turns out that there are other settings where somehow the tails can look quite very different. And in fact, then if the tails look different, then the black hole interior will also look very different. So this is just an aside to really tell you somehow to understand tails on the exterior has a lot to do with the interior. Things can get very, very different. So here's an example of a result. So you can look, there are 2 different results of Maxime van der Motel and Warren Lee and Maxime van der Motel, which tells you that they can construct black hole interiors. They solve the Einstein's equation with the appropriate matter field. They bifurcate off Rice-Nordstrom, which I haven't really told you what it is, but you should think of that as a spherically symmetric proxy for Kerr, so it has a Cauchy horizon. But you can bifurcate off something with a smooth Cauchy horizon, but if you don't have decay, if you don't have any tail, okay, so no decay whatsoever, then you can construct some examples for which the black hole interior actually has a strong space-like singularity. So you can have something that the interior looks completely different, more like Schwarzschild than like rotating Kerr. Okay? It turns out that there are other examples where you would be interested in situations where the tail is very slow. For instance, one case which slow tails naturally arise, it would be in asymptotically ADS black holes, what we just saw in the last talk. And in fact, there will also be a talk exactly about this problem tomorrow. Okay? Well, of course, there's a funny story about very slowly decaying tail. There's actually also an interesting story about very fast decaying tail, which I'll also not have time to talk about. And if I guessed correctly, the talk of Hollands on Friday will tell you a little bit about it. Okay, so that's just an aside, and I want to come back, and I want to think about tails on asymptotically flat backgrounds in odd spatial dimensions. Okay, so here's the plan. So as I said, I will first give you some examples, okay? And then before I formulate the theorem, so I want to have some particular examples that I would like to think about for which I can understand precisely the late time tail. Okay, so I will start with things which are stationary for the reason that they are maybe slightly more familiar, and in any case, they have been understood first. Okay, so the story of tails on stationary backgrounds, one place to start is this celebrated paper of Price. And this is where sort of this half decay with the name of Price's law comes from this paper of Price. So what he tried to understand is the following. What he tries to understand is you want to look at a wave equation on Schwarzschild spacetime. So remember, we have looked at Schwarzschild earlier. We have drawn the Penrose diagram. And you can try to look at wave propagation on exact Schwarzschild. So what he suggested is the following picture. Okay, look at solutions to the wave equation. Okay, so this is just a down version on Schwarzschild, and look at, let's say, very, very nice initial data. And let's say, look at, because Schwarzschild is strictly symmetric, I can decompose my solution in spherical harmonics and look at, let's say, things which are supported on spherical harmonics of degree L. Okay? So then if you look at, let's say, a fixed R, so fixed, let's say, compact spatial region, and try to understand what happens to the tail. And what he suggested was that generically what you see is a tail of exactly this type. Okay? So if your L equals 0, this is t to the minus 3 decay. Okay? This is already very different from what you see on Minkowski, where you have no tail in the Schwarzschild case. Once you turn on mass, you have t to the minus 3. And in fact, if you look at spherical harmonics higher and higher, the decay rate is faster and faster, depending on L in this particular way. Okay? So this was suggested by Price, and now it's a theorem, and it sort of has a long history, even sort of the mathematical world. There's a long history in the development of the theorem. So the first thing that was understood were upper bounds. Okay, so remember the way at least I wrote it. This is upper and lower bounds. Of course, this is for generic data because 0 is a solution which has no lower bounds. But for generic data, one expects something like this. So the first thing that was understood was upper bounds. Of course, this holds true for any data. There's no genericity. So there are first works of Dunfermline-Swarnianski in spherical symmetry with a little bit of loss, and then this was first established by Dorninger, Schlag, Soffer, and Tataru, and there's also another proof by Metcalfe, Tataru, Tornalu, which actually is a bit more general. I'll say a bit more later. That applies certainly not just on Schwarzschild, but in fact also on dynamical setting. So this is the statement about the upper bound when L equals 0. Well, in fact, you can sum over all modes, and you can still get this bound. And if you want to think about things which has spherical mode dependence, I want to say that, well, if L increases, then you have more decay. So there's a result with a slightly slower rate, t to the minus 2L instead of t to the minus, instead of t to the minus 3 minus 2L. I want to go back to show you that, but I couldn't. Right. Okay, but this was established in the work of Dorninger, Schlag, Soffer. And finally, more recently, somehow the generic case with lower bounds, sort of everything was understood. There was two different approaches. One is approach by Angelopoulos, Tagus, and Gaich, and the other is the approach by Hinz. And what they showed is in fact, you can write down an exact term which has the expected price decay, and whatever error, it decays faster. Okay? So, in fact, this is not just a statement about Schwarzschild. In fact, you can look at Kerr, right? Everything that said about the t to the minus 3 tail. Right here, you can't, because Kerr is not strictly symmetric, you can no longer decompose into spherical harmonics, but you can look at the full solution, so the t to the minus 3 tail will still hold on Kerr. And in fact, the techniques in these papers, they are more general. They can really be applied to more general space-time for which you can have sharp decay. So one of the things you can say, for instance, you can read off from the theorem I'll show you later, is that you can look at stationary asymptotically flat space-time, and for this statement, stationary is important. And you can just look at the class of metrics for which you have certain decay at infinity. And suppose you have certain good control of wave propagation, let's suppose you have some integrated local energy decay, then one actually can establish some tail result. So let's look at this. If you look at Schwarzschild, Schwarzschild has the case that the difference decays like r to the minus 1, so alpha equals 0. So in this case, this is t to the minus d. In d, when d equals 3, this is exactly the price law decay you see here. Okay, but this is more general, and if you have more decay of the metric at infinity, you get faster decay. So these upper bounds in the stationary setting, they are known in these works cited. But in fact, what is true is that if you look at generic space-times which satisfy this sort of bound, they have this sort of approach at infinity, then in fact, for generic solutions, you actually have this exact tail when with z equals 0. Okay? And here somehow there's a funny thing, which is genericity is really important. You can't just look at any stationary space-time with this approach. There could potentially be certain cancellations so that you have faster decay. And in fact, this type of cancellation do come out in physical settings. You can, now we're still within the setting of stationary things. You can look at high-dimensional Schwarzschild. I've written down for you the explicit solution. Oops. Explicit solution for Schwarzschild. Okay, so this, when d equals 3, it's maybe the more familiar Schwarzschild, but in high dimensions, there's also a solution to the Einstein vacuum equations. Now you can look at higher d, right? Let's say d equals 5 and so on, right? And I've told you sort of how to compute decay, right? This is, I want to understand, so the extra decay that I get beyond the d will be alpha, and alpha is how much beyond 1 you have. So here you have d minus 2, so it's d minus 3 more than 1. So you might expect that you have minus d minus d minus 3, so minus 2d plus 3 tail. But in fact, on high dimensional Schwarzschild, one thing that follows from what our theorem that I'll show you later is, in fact, there's a cancellation. So if you look at d equals 5, right, minus 2d plus 3 is, if I've done it correctly, minus 7. But if you look at Schwarzschild, in fact, the correct thing is minus 10. So even in the stationary case, there can be subtle cancellation, and it happens here. And this is not something that we first observed, at least sort of heuristically. It has been observed previously in high-dimensional Schwarzschild by Cardoso, Yoshida, Diaz-Limos, and also Bizon, Shark, Petrowski. Okay? And a similar phenomenon holds not just in d equals 5, but all higher odd dimensions Schwarzschild, you see this sort of phenomenon. Okay, so these are a class of examples, sort of first with price and generalizing price law on stationary backgrounds. So now, again, because finally what I want to understand is I want to understand strong cosmic censorship. Let me try to understand something on dynamical background. Okay, so let's move on to dynamical background. Okay. So, well, the first setting you can think about with dynamical background is, let's suppose you have something that converges to Kerr. Okay? Oh, sorry, I didn't do it correctly. Kerr including a equals 0, so including Schwarzschild. Okay, so you can look at this, and suppose you look at nice data, and what we can show is that the result of t to the minus 3 that you saw for exact Kerr, exact Schwarzschild, still holds in this case. If something just converges to Kerr, well, it can, with some polynomial rates, it can be very slow. Here, again, upper bound is known, including in the dynamical setting in the work of Markov, Tataru, Tornano. The new thing is about the tail, which is the exact tail, which is this, which holds even in the dynamical setting. It turns out there's something amusing that happens, which is, well, in this case, there's nothing different, right? Okay, the result is really the same, except for the assumption where you allow something to be not exactly Kerr, but just converging to Kerr. But it turns out there are cases for which, if you look at dynamical situation, it's different. The answer is actually different from the stationary case. So here's one of the examples you can think about. So now let's not look at something converges to Kerr. I want to look at something converges just to Schwarzschild. Okay, a particular example with angular momentum equals 0. The reason I want to think about this is I want to assume something that's strictly symmetric. Okay? And now I want to think about something converging to Schwarzschild, and I really want to think about something that's not exactly Schwarzschild. Okay, so Schwarzschild, of course, is converging to Schwarzschild, but I want something that's really dynamical, and I want to capture this by saying that if you look at Bondi mass, the infinity is not constant. Okay, if you are Schwarzschild and the constant, I want something that just converges to constant. It can converge very slowly, but as a polynomial, it can converge like very, very fast. It doesn't matter as long as it's not constant. Then this applies. So what do I want to understand? I want to understand solutions to wave equation, and I want to look at solutions supported on spherical harmonics bigger than or equal to L. Okay? In particular, I can also take L equals 0. That would be the full solution, and that would be the case in the previous slide. So what's the tell here? So as I've just told you, if I look at L equals 0, so that's the full solution. So that would be what you see in the previous slide. So then generically, you would have something that looks like t to the minus 3. Okay? But if you look at higher spherical harmonic, then you see something that you can also get the precise tail. So you can get you can extract the main term and say the error term decays better. But then what you see here It's not the Price's law, which is t to the minus 3 minus 2l, right? Look at if l equals 1, these two don't match, right? But something slower. And this slower thing comes from the fact that you are actually dynamical. You are not stationary. So this is right. So contrast this with the t to the minus 3 minus 2l Price's law, and there have also been indication of this in the physics literature in numerical experiments in the work of Bizon, Shaffer-Chorovsky, and Gunnar, Price, and Pullen. Okay. And I want to say one thing, which is this type of phenomenon is nothing about sort of spherical symmetry per se. Of course, I need spherical symmetry here to make the statement because I have to decompose the spherical harmonics. But this type of results have analog if you look in high dimensions. So if you want, this is sort of a higher spin type phenomenon. If you look in high dimensions, you can look at you can find dynamical spacetimes, so not stationary, and you will see that you will have a decay rate which is slower than what's predicted by Price's law. Okay, so this is a general phenomenon. It's just that in d equals 3, l equals 0 is a special case where you don't see this. But when L is bigger than 1 in spherical symmetry, or if you look at general spacetimes in sufficiently high dimension, then you will see that dynamical things on dynamical backgrounds wave decay slow. Okay, so maybe already at this point I can try to connect this back to sort of the original motivation, which is the strong cosmic censorship conjecture. I told you that what I really want to understand is a convergence of Kerr to convergence of perturbations of Kerr to Kerr. Well, I want to understand the convergence rate. And I also told you that these I should think of as high spin equations. I should think of this, for instance, in L bigger than 2 problems. So if I think of this as L bigger than 2, one of the consequences one may think, if you relate back to the question of perturbations in the context of Einstein's equation, is that well, if things are dynamical, you would think that the decay rate has to change, right? Like what we just saw, instead of minus 3 minus 2L, it's minus 2 minus 2L, so when L is 2, that's minus 6. So one may conjecture that if you look at small perturbation of Kerr, right, the tail that you want to look for in order to establish strong cosmic censorship would be t to the minus 6. This would be different from Price's law prediction. Of course, Price's law prediction, okay, you should think it's really for Tchaikovsky, and okay, this is a nonlinear thing. Okay, there might be something to think about, but let's, for the moment, formulate the conjecture like that. And if you know this is the tail that you want to shoot for, okay, let's say this is true, then you want to say, well, okay, maybe once you have this type of tail, you can really understand the interior of the black hole. In particular, one may also conjecture that if the exterior region converges to Kerr with an exact rate of like t to the minus 6, then in fact the Cauchy horizon in the interior is also weakly singular in a certain sense. Okay? And the second conjecture in particular is really strongly suggested by linear analysis by Spiersky and Marjan. Okay, so I've said enough about sort of examples of tails, but I should really give you a theorem on how to compute the tails if you give me a general dynamical, potentially dynamical nonlinear setting. How do I understand what should be the tail? And I want to derive sort of things that I showed you earlier from the theorem. Okay. So how am I doing on time? Okay, so how should I think about tails? So here's how I want to think about tails. I want to first think about tails from the Minkowski point of view. Okay, I want to think about Minkowski. You tell me, wait, are you not crazy? Because you just told me that on, well, not just, but okay. 15 minutes ago, you told me that on Minkowski there are no tails. So what do you mean when you say you try to understand tail by trying to understand Minkowski? So here's what I'm telling you. So first, let me repeat what I just said earlier. If you're on Minkowski, if you look at compactly supported data, of course, there's no tail. Okay? But of course, on Minkowski, you can have tail. You know? And the way that you can have tail is if you put tail in data. Okay, I'm not going to use the sophisticated eraser. So let me just do this. So what can happen in Minkowski? What can happen in Minkowski is that, well, if you put in data, let's say if you look at the characteristic data on a cone, okay? And let's say, suppose I look at 3 dimensions. And suppose on the cone, I put in already some tail, okay? So I look at R5, it's like r to the minus alpha. Okay, alpha is integer. Then it's possible that I would have a tail because I put a tail in. Okay, and this tail I can compute explicitly what this tail is. So in fact, I know that if alpha equals to, let's say, 0, 1, 2, and so on, I can do an explicit Minkowski computation, and I can tell you what tail I expect if I just look, let's say, along a curve of constant x as t goes to infinity. Okay? So it turns out that what you have is that if alpha equals 1, you get the decay of t to the minus 2. If alpha equals 2, you get a decay of t to the minus 3 in d equals 3, and you can continue, and you can do this explicit computation. There's something very amusing, which is alpha equals 0. This is actually anomalous. If you do this and you try to compute the tail, in Minkowski, there's no tail. Right? No tail in the sense of things become 0, right? Like strong Huygens. So this is the Minkowskian tail. I want to think of it like that, right? Because this is the only Minkowskian tail that there is, because there's strong Huygens principle. Okay. So once I understand this now, how do I understand sort of tails in general? What I want to do is the following. So let's say I want to understand, let's say, Price's law and tails and so on, everything like in the following way. So first of all, I want to look in my space-time in a very, very far away region. Okay, I look in R, very, very large region. And I want to look at, let's say, an RU coordinate. R is the usual R. U you can think of as T minus R. In RU coordinate, I want to first say that if I look at a very far region, I can look at my solution. I'm still in 3 dimensions, right? R phi. I want to say I can write down expansion like this. Okay, so this is part of the thing that I'm going to prove. Okay, I'm going to prove that I actually have some expansion like this. Okay, and then I analyze this expansion at infinity. Okay. So now I analyze this. What do I want to look for? I want to look for the smallest I, that is to say the first term in the expansion, with the following property. First, I want the property that I look at that I, let's say this one, phi 1. I want to look at this so that at null infinity, if I take also, so I already looking at, so this is a term where if I go r to infinity, decays r to the minus 1. I look at this term and I want to look at u goes to infinity. And I want to look at the first term for which when u goes to infinity, you have something non-zero. Okay, you get some non-zero limit. Okay, and then, well, I want this I to be such that this gives a non-trivial late time term Minkowski, something like that. Okay, so in d equals 3, I want to say about something that's not alpha equals 0. Suppose I have something I equals 1 or I equals 2. Suppose I have a limit. Okay, then I want to say the tail that I inherit in a finite R region is exactly whatever tail I see here. So now I can sort of state something that resembles a theorem. So this, again, joint work with Sungjin paper still in preparation. So think of a wave equation. So it can be quite general. Just think of P is the linear part. Of course, I'll have some conditions in a minute. And N is some nonlinear part. Okay, it can even be quasi-linear. So it can depend on 2 derivatives. D has to be odd dimensions. And here are sort of a not very precise list of assumptions. So first, you want to say, well, this is asymptotically flat. Okay, so if R goes to infinity, things look like Minkowski. And moreover, there's a sense that you become stationary. Things are dynamical, but it has to become stationary. So as t goes to infinity, you become stationary. Okay, there are certain rates assumed, but let's not be precise here. And if you are in d equals 3, there are certain conditions you need for the nonlinearity related to well-postedness of the problem, which are known as the null conditions. So if d equals 3, I have to assume that as well. And 3 and 4 are sort of the more serious assumption. Okay, so let me try to first explain 4. Okay, so what I want to say is this is not a completely unconditional theorem. I want to prove a theorem which says, right, as I sort of stated it in the very beginning, I want to have a theorem that says that, well, suppose you give me some decay already. It can be very, very weak. So in fact, if it's a linear equation, this weak decay can even be growth. Not growing not so fast polynomially, but you have to understand this not just the solution, but also suitable factor field bound. Okay, so if you if you want B estimates. As we learned from Dean's talk yesterday, it's better maybe not to be precise about those. So these are assumptions. So I already assumed the solution decays, and I want to understand the precise decay. And then there's the assumption 3, which is the following thing, which is if you look at P, this is the wave operator, but forget about all the dt terms. Okay, so if you want, if you can think in the stationary setting, you can take Fourier transform in T and look at the frequency 0. That operator, I call it P naught, but now this you can talk about even in non-stationary setting, just drop all the dt terms, okay? And I want this, you can think, for instance, if it's the usual inversion, this P naught is just Laplacian. You can think this is roughly an elliptic operator, though in the black hole setting it's slightly more complicated. I have to assume that this is invertible with some estimates. So if you want, this is sort of some estimates about the absence of zero eigenvalues and resonance. And inside this assumption can hide a lot of things, right? So inside, I can allow for lots of derivatives, etc. Inside this assumption can hide everything about trapping superradiance and so on. But these are all my assumptions, okay? So I already know that I have certain good structure about my operator, and I already know a little bit of decay of my solution. Then the theorem tells you that you can compute the late time tail in exactly the way that I told you how to compute. Now, more generally, previously I have d equals 3, for which d minus 1 over 2 is 1. But more generally, you can look at this and you expand right, near infinity and try to understand what happens when you look at the corresponding Minkowskian problem. And then you get the decay rate. And then there will be also a spatial dependence that has to do with thinking about this operator P naught. So let me say the theorem again in third time. So this is how you determine the late time tail. So the result tells you that phi you can write down as some main term plus error. The error decays faster. So the main term has sort of 3 things to understand. One thing is the decay rate. Okay, so this is the decay rate, t to this. The second thing is the spatial profile, how in space, what's the profile, and then there's the coefficient. Okay? And how do I determine all these things? So again, I would just look at the expansion of this at infinity. I would have to, well, I first say that part of the theorem is that this expansion makes sense. And then I try to analyze this. And I have to first compare with the Minkowskian picture. The Minkowskian picture is such that there are certain things which have no contribution, right? In the 3D case, this has no contribution. In the general dimension, the first few terms, they don't contribute, okay? So whatever decay rate you would get has nothing to do with the first few terms, okay? So now you look at the terms which are beyond this, okay? So the terms which are at least d minus 1 over 2, the next term after d minus 3 over 2. So look at the smallest integer, as I said, look at the smallest such that this is non-zero, okay? So this is still a function on the sphere after you take limit u goes to infinity. Now take the spherical average. This is S naught L, okay? So that's the coefficient, has to do with whatever you analyze at infinity. And then the rate would be t to the minus j minus d minus 1 over 2, and this j is this j, the smallest integer. Okay? And so this determines the rate, and the spatial profile has something to do with this, and you have to solve certain, think of this as elliptic equation. Okay. So that's in general how you determine the late time tail. And you can also sort of think about high L modes. There's a similar result, which looks similar as before, except now if I have high L modes, okay, the decay rate would be faster. Right? I have 1 extra power of L. And everything else is sort of similar, right? Let's just look at 3D for simplicity. You throw away things which don't contribute. Now look at the things that contribute. Look at things which does not converge to 0, and then that gives you the coefficient, and then the decay rate is this, and then the spatial profile you solve some elliptic equation. Okay, similar theorem, and then the error term decays faster. Okay, so. Let's already make an observation here. So, of course, I have already told you that in general, the first few terms don't contribute. Right? You would not have tails. It has to do with this sort of phenomenon. So, because the first thing that can contribute would be j equals to d minus 1 over 2, and I also know that the tail is is minus j minus d minus 1 over 2. Right, it's minus j minus d minus 1 over 2. I'm a bit out of lecture. Right, it's minus j minus d minus 1 over 2, but j has to be at least d minus 1 over 2. So at least I would have dk minus d plus 1. Right? So I can always have this. So, and there's a similar argument you can make for strictly symmetric spacetimes to tell you that you must have decay at least t to the minus 2L. Okay? And in fact, these rates, they can already be achieved on non-stationary backgrounds. You can find non-stationary dynamical examples for which you exactly achieve these rates. And these rates are slower than the Price's law rates, where the Price's law rates tells you that in the first case, you have t to the minus d. In the second case, you have t to the minus 3 minus 2L. And one can, if you want to think about it like that, you can think of stationary tail, something like Price's law, is some improved decay estimate originated from some cancellation. I'll try to show that cancellation in a minute. There's something amusing about this particular rate, by the way, that's t to the minus d plus 1. This is exactly the rate that you see in even dimension. Right? So in dynamical setting, you can achieve a rate which is the same as the rate as even dimension. And furthermore, I told you that on higher dimension Schwarzschild, right, there's further cancellation, and you can also read it off by trying to understand sort of the further cancellations in the expansions at infinity. Okay, so I have a few more minutes. Let me try to use this theorem and try to derive what I have tried to set earlier in the example. Okay. So the first thing to try to understand is to try to understand what happens when things converges to Schwarzschild curve. This in particular includes things which are exactly Schwarzschild curve. Okay. So what do? I write down the wave equation, assume an expansion. Okay. So the theorem will tell you that okay, you can actually justify an expansion, and then use the wave equation. You can try to understand these phi i's. Okay. So you understand this phi i's, and you can look at something asymptotically Schwarzschild curve. And you can try to analyze what happens. Okay. So the first thing I told you in d equals 3, right? The first term doesn't do anything, right? I mean, alpha 0 is there's no tail, so forget about phi 0. I want to understand what phi 1, phi 2, what's the first thing that contributes. Now it turns out that whether you are exactly Schwarzschild, exactly Kerr, you will have or asymptotically you would have these. Recurrence equations. In particular, derivative of u1, derivative of phi 1 is 0. So phi 1, because everything is compactly supported, it's always initially 0. So phi 1 is always 0. Okay. And now you look at phi 2. du of phi 2, of course, is phi 1, but phi 1 is 0. So you have something that has phi naught, and you have to look at the integral of this. And one thing that you can say is that you can prescribe phi naught. Essentially prescribe it up to small error. And therefore, generically, you expect that you have an expansion that looks like this. You miss the r equals r minus 1 term. You only have the r minus 2 term. And because you have r minus 2 term, you read off the decay. That should be t to the minus 3. Okay? So that's the origin of the decay on things which approach a Schwarzschild curve. But now I want to show you that if you look at L equals 1, there's a difference in what you can see if you are dynamical or if you are stationary. And here is sort of a cancellation that you can see that's related to Price's law. Okay, so let's look at phi L equals 1. Because L equals 1, I told you that there's one more that doesn't contribute. Right? So phi 0, phi 1, you don't have to think about that. I want to understand phi 2, phi 3, which is the first one that doesn't go to 0. Okay. So you can write down the equations. These are the equations with some constants C1, C2, which okay, the exact values are not so important. Well, okay, it may be a bit important in a minute, but okay, so let's do that. So first I want to try to understand whether phi 2 would go to 0. So this is the integral of m of phi naught. But turns out there is a cancellation, and this is sort of the origin of Price's law. I mean, this way of thinking about it, which is okay. You have du of phi 2 is some constant times phi naught, but phi naught you can write it as du of phi 1. Okay, so I can combine these two to get this equals 0. But of course, everything is initially compactly supported, so that means phi 2 is a constant multiple of phi 1. But phi 1 is something that I don't have to think about. Phi 1 is something that would always decay, so therefore phi 2 also has to decay. Okay, so there's this cancellation that happens in this case where your Schwarzschild is L equals 1. In general, you can then go and look. Phi 3 actually does not go to 0. You can actually compute du of phi 3 is some constant times phi 2 plus some constant times phi 1. Of course, phi 2 already tells you it's some constant times phi 1. I've derived that. So this overall is some constant times phi 1. Turns out C2 has the value so that these two things do not cancel. So then you have du phi 3 is equal to some constant times phi 1. And that integral, in general, is non-zero. Again, there's a similar phenomenon. Phi 1 is you can essentially prescribe on null infinity, and therefore it's not zero. So the main term that you see comes from phi 3, and therefore you have t to the minus 5 for L equals 1 on Schwarzschild. Okay. Now, what changes if I am not exactly Schwarzschild, but I have something converging to Schwarzschild? So again, I look at L equals 1. Again, I would have similar recurrence equations. The only difference is that m is now no longer a constant. I have prescribed that m has to have non-constant Ponti mass. Okay, so this is not a constant, it's a function of u. So the derivative is non-zero at some point. Okay, so what's the difference? So if it's not a constant, now you look at phi 2, I integrate, right? So I have to integrate m times phi naught. I play the same trick. I write phi naught to be derivative of phi 1. But now I have trouble because I want to integrate this away. But the best I can do is integrate by parts and put the derivative of m. But m prime does not have to be 0. So in general, because you can prescribe phi 1 as you wish, this does not have to be 0. So you might have generically, in fact, phi 2 to be non-zero. So this gives a slower t to the minus 4 instead of t to the minus 5 decay. So I think I'm already over time. So let me finish here. But if you have any questions, I'll be happy to explain the ideas of the proof.